Hello, everyone. I'm going to try and give you a flavour of some of the technical detail behind design for performance. The underlying thing is that it really involves a complete change in mentality when you're designing a building. And I think nothing illustrates this better than if you think about when a building is actually, the construction is completed, the building is handed over, and you have a year when you go into a defects liability period. If you're doing a design for performance project, the objective during that year is to get the building to perform as you said it would. Whereas in a design for compliance regime, you are basically trying to say that the building is compliant with the specification. And those two things are completely different and will hopefully demonstrate totally different results in performance outcomes. So I'm going to run through quickly why we so desperately need design for performance, what it involves, some of the results from the pilot studies that have been completed, and lastly, a little bit of detail of what it involves for the M&E engineer, who is very fundamental to delivering design for performance. So why is design performance so needed? Start with this statement, and by following the process in a neighbours commitment agreement, Australian teams can now routinely achieve in-use operational energy performance ratings in line with the predictions of design stage models. So it is now routine in Australia to achieve buildings performing as intended. And I think all of you will recognise that that is not the situation we find ourselves in the UK. Now let's look at what has been done in Australia. This line on this graph shows the relationship between the energy use, kilowatt hours per square metre, and the star rating that Sarah's already told you about. So you've got a very high energy use at the top left for a 1-star building, and a very low energy use at the bottom right for a 6-star building. And in the early days, it was a 5-star scale, which was set using empirical data so that the median performance was 2.5 stars, halfway along the scale. So we know that in 2002, the average rating for buildings was 2.5 stars. Now, I'm going to talk about Melbourne. You'll see Melbourne there, because the climate there is as close as we can get to London. It's not the same, but it's similar. It's a lot hotter in summer. It's not so cold in winter. It's close enough. So 2.5 stars in 2002. 2018, the minimum standard for new build in Australia is 4.5 stars. The average for new build is 5 stars. And this is not driven by mandatory requirements, a MEES-style requirement. This is driven by the market. Tenants are just wanting a 4.5 or 5-star building as a minimum. The best buildings in Melbourne are now achieving 6 stars, which is halfway from 5 stars to 0, real 0. This is not a mirage UK 0 that we had in up to 2016. So it's been a massive market transformation of buildings in Australia, driven by this the process that we are now trying to replicate in the UK. I want to say the kilowatt hours per square metre on this graph relates to a specific part of the building energy use. So if you look at the total energy used in a building, which is what you would rate for a display energy certificate, what the Australians have done is separated that out between the whole building HVAC, hot water, the lifts, and all the energy used in the common parts, and that is called their base building. And the rest of the energy, which is the responsibility of the building users and occupiers, as things like the tenant's lighting and small power, is separated out. And they have a rating for the base building, which is what the graph on the previous slide was relating to, and then individual tenants can get ratings for their energy use. So you're essentially delineating the energy use between the actors who can actually do anything about it, have the agency to improve it. So if we come back to this graph of the market transformation in Australia, the obvious question is, where do UK buildings sit on this graph? And the answer to this question is we don't know, because we just don't measure it. It is actually scandalous that, for the last, well, forever, but certainly over the last 20 or 30 years, we have not been measuring the performance of our buildings in use. We did a limited exercise to try to find out from some of the buildings that are owned by BBP members in 2012, and it looked like from that data that the buildings in London are using a very similar amount of energy to the buildings in Melbourne back in 2002. So if you look at it in energy intensity terms, the average building in Melbourne is using 3 times less energy than the average in London. So this is not an aggregation of marginal gains. This is just a mind-boggling difference. So what are the reasons behind this change? And there's essentially 2. I'll go through these quickly. The first one, Sarah has already alluded to, and it is this virtuous circle where the occupiers have learnt that a better rated building is indeed a better building. So they are asking for better rated buildings. They're actually prepared to pay a premium rent for better rated buildings. That creates an incentive for investors to call for better ratings. Developers are then obviously going to try and produce better rated buildings, and the supply chain is required to deliver better rated buildings, and eventually the letting agents will recognize that better rated buildings have a rent premium and a value premium, and the whole thing goes round and round in circles, and it's win, 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 win for everybody. So the second reason that Australia's had their success is obviously they've had to do something to reduce the amount of energy their buildings use by a factor of 3 on average. And this is what the ingredients that they've learnt to introduce into their building design process. Now, the reason that they did this is that the developers of new buildings needed to be in control of their performance once they were made available to the market, because they were then going to be competing with existing buildings that already had ratings. So they wanted to be sure that once their building was operating, they knew what rating it was going to have. They wanted to ask their designers to create a building with the right rating. And the process for them to do this is what is coming up on this diagram. So the first thing they do is ask for the target rating that they want, 4 stars, 5 stars, whatever. They integrate that target into the requirements for the whole supply chain. They use much more advanced computer simulation to ensure that the building is going to perform in the way that is intended. So they essentially create a digital twin before it's constructed. They then have this independent design review process where the reviewer checks that in their expert view the building will deliver the target. Once the building is constructed, it's not that these buildings hit the ground running and don't need any fine-tuning. There's an intensive process of fine-tuning. Very critically, once the building's been in operation for a year, they have a accredited process for measuring, rating, and disclosing the base building performance. And last, and definitely not least, that rating, by being made available to everybody, but including the designers, creates an invaluable feedback loop so that people know, did their design actually work? And that's obviously for investors, occupiers, developers, and everybody. So there's a lot to do to get this right. I'm sure the font size on this is going to be fairly illegible from the back. But this shows the different actions that need to be taken at each stage of the REBA plan of work, and indeed the BISREA soft landings process. I want to focus on the role of advanced simulation. And it's absolutely critical for the building to perform as intended that the HVAC system and its controls are included in the simulation. And that it fundamentally is the difference between what they do in Australia in terms of simulation and what we do here. And I'm talking here about level 5 simulation for larger or more complex buildings, where you are using a dynamic model, but you do not put into that model the time-step by time-step performance of individual plant. Now, another thing that they do in Australia essentially is to write a draft of the description of operations for this building coming out of their modelling. You don't wait until the building is constructed and work out how is this building working. You do it in advance, and that is then fed into the control engineer brief so that they can create the control system according to how the model says it should be. So you build and commission the building to match the design which is represented in the model. You may revise the DesOps with any differences between the actual building and the original design. Once the building's in operation, you use the results of the model as a framework for tuning up the building. So the building should be performing as predicted by the model. And there is a process of looking at the sub-meter data for the building, checking how the real performance of this building compares with the predictions, diagnosing improvements or things that aren't working exactly, making sure that the building rating is on track to what it's supposed to be. So that gives you a flavour for how the modelling is such a key part of the whole process, running all the way through from potentially stage 2 right through to stage 7 of the process. It's not just a backroom compliance check that we do here. So moving quickly on to looking at some of the pilot studies that we've done. There were 6 main projects that completed full pilot studies, and you can see that 5 of them undertook some advanced simulation, 3 of them had independent design reviews, 3 of them have been looked at in use, and 3 of them indeed have got actual measured ratings. Now, looking at 5 of those pilot buildings, you can see that for 4 of them we got a predicted rating, and for 3 of them we have a measured rating. There's only 2 that we've got where we have ratings for both measured and predicted. That's purely because we only had a 2-year window for the pilots. I'm going to tell you a couple of little anecdotes about the 2 pilot studies where we've got both measured and predicted ratings. So this pilot study here, the 3rd bar down is the measured base building performance of this building. It's labelled 5ES, that's the name of the building, acronym. And we're comparing it here with the Energy Consumption Guide 19, which hopefully some of you have heard of, guide to benchmarking the energy use of offices. Now, there's 2 things that stand out from this graph. The first, I think, is that this building is better than good practice, according to this benchmark. We note that the typical performance is minus 1.3 stars, so compared to Australia, it is awful. The second thing I'd like to show is that the target for this building is 5 stars, and we do hope with some intensive fine-tuning to bridge that gap between 2.5 to 5. I don't think we'll get to 5, but we might get to 4. That process couldn't happen during the first year of occupation because essentially the contractor was insistent that we couldn't touch the building if it impacted on their ability to get the building signed off with no defects. The second anecdote is looking at a building where we applied design for performance to an existing building that was undergoing potentially a refurbishment. And we did some advanced modelling, and very briefly, this graphic here shows the energy use for each hour of January. This is the modelled performance, and it's the energy used by the chiller. So this work was done by somebody called Darren Coppins, and his first comment was, why on earth is the building using the chiller in January as part of the design? Well, it is, and that's, that is what the design says should be happening in January. This is the measured data for January. Now, you're not children, we don't need to play spot the difference here. We're basically looking at the difference between order and chaos. And this building should be performing according to the model. And there's some things that are very badly wrong. Now, some of that bad control has been put right. And particularly the fact that chillers coming on between midnight and 5 a.m. Was a fault in the control system. But we've only identified it by doing this side-by-side comparison. So I want to finish in a very quick order with some comments about the role of the M&E engineer in delivering design performance. And the responsibilities for the M&E engineer that differ from the current responsibilities: doing this advanced modeling, being responsive to your independent design review, having a much more extensive commissioning and fine-tuning process, including the BMS reviews, measurement and verification, and tracking of the rating. The objectives of the simulation, this is not just a compliance check. You're trying to confirm that the building will achieve its target. You need to identify where to put the meters for a validation plan. You want to generate targets for every meter that you're putting into the building. You're trying to optimize the control and get it to work in the model, then you can get it to work in the real building. And you're trying to understand whether the plant capacity is appropriate, because the use of advanced modeling can actually lead to cost savings by understanding you don't need as much capacity as most buildings in the UK have, because they just don't test the design under realistic conditions. And lastly, the building is supposed to achieve its performance whatever the occupants throw at it in terms of hours of use and density of occupation. So the design engineers have to test the design under what the Australians call off-axis scenarios. So this is intended to prove the resilience of the design to different types of tenant that might occupy the building. I shall go quickly now because I think I'm running out of time. The independent design review is done by a very special expert who understands HVAC design, understands simulation, knows about tuning up buildings and auditing buildings for energy efficiency. They identify risks and opportunities in the design, and it's a very interesting way to upskill the industry, which is part of the role of, as Sarah mentioned, of the design for performance projects. So I think on that note, I can come to a close.